In this video, we're going to look at how you can use the unit circle to derive three Pythagorean identities. So I've started by drawing a unit circle, and I've shown a completely arbitrary angle theta that will correspond to coordinates x and y for the terminal point of that angle. And knowing that we're looking for Pythagorean identities, it's a safe bet that we're going to use the Pythagorean theorem. So we have to have a right triangle, and I will draw that right triangle here, pull the triangle out, and then I'll start to think about the lengths of the sides and the length of the hypotenuse to get some identities. Looking at this triangle, I want to remember that the hypotenuse came from the radius of the circle, and since this was a unit circle, my hypotenuse has to equal 1. The altitude of the triangle is just the height over here, which corresponds to the y-coordinate, and likewise the base of the triangle will be the x-coordinate. Once I know the two legs and the side, I can use the Pythagorean theorem, which just says leg squared plus leg squared is hypotenuse squared, a squared plus b squared is c squared. And if I write that out, I'll have, in this case, y squared plus x squared is equal to 1. The next thing that's going to be really useful to remember is that x and y were equal to some of my trig functions on the unit circle. In particular, the sine of theta was defined to be the y-coordinate on the unit circle, and the cosine of theta is defined to be the x-coordinate on the unit circle. Knowing that, I can make a substitution. I know that y is equal to sine, so y squared must be sine squared of theta. I know that x is equal to cosine, so x squared must be cosine squared of theta, and my 1 on the right-hand side is going to stay unchanged. So this is actually the first of three Pythagorean identities that we have. So I'll pull this over to the right, and we can talk about what we can do to get two of the other trig functions, or Pythagorean identities, excuse me. The way I want to approach this is I want to think about how I could get a Pythagorean identity that has a tangent squared inside of it. And the way this is going to work is I want to relate tangent to the sine and cosine functions that I have over here. In particular, I know that tangent is equal to the sine of theta over cosine of theta. And since this is tangent squared, I need to have sine square and cosine square. So this is what I'm looking for in my identity. I need to have a cosine square in the denominator, and I can force that issue here if I simply divide both sides of the equation by cosine squared. And I can do that term by term. So my first term, sine square of theta, I'll divide that by cosine squared of theta. My second term is cosine square of theta, I'll divide that by cosine squared. And likewise, the right-hand side is currently 1, divide that by cosine squared of theta as well. When I do this, it kind of looks like I've just made a big mess, but things are going to simplify pretty nicely. This first term, sine squared over cosine squared, a minute ago we said that this was equal to the tangent square of theta. And then cosine square over cosine square is equal to 1. This will be equal to, this is the reciprocal of cosine squared. The reciprocal of cosine is secant, so this is the secant square of theta. So that gave me the second of the three that I need. Again, I was looking for tangent squared, figured out what the denominator needed to be, and I made it happen. So the next one we're going to look at then is going to be kind of a similar idea, and you'll notice that I have 4 of the 6 trig functions here. We're missing cotangent, we're missing cosecant. So I'm going to think about what I could do to, say, get cotangent square of theta. Same idea, I want to relate this to sine and cosine. Cotangent square is cosine square of theta over sine square of theta. So I'm going to divide both sides of my equation by sine squared, but I'm not actually going to do that the exact same way I did it before. And the reason is that when I have my students use these identities, I always recommend that they take the first one, sine squared plus cosine square, write it off to the side, and derive the identity they need every single time. And I'm going to do this with some shorthand. So the big one that I'm looking at is sine squared plus cosine squared is 1. This is my shorthand again. and I need to get sine squared in the denominator, so I'll divide everything by sine squared, by s squared. When I do that, same simplifications will happen. Sine square over sine square is 1, plus cosine over sine is cotangent, so that's the cotangent square of theta. And 1 over sine squared is, let's see, 1 over sine is cosecant, so 1 over sine squared is the cosecant square of theta. So this will be the third identity that we need. I'd write that over there. And I'm going to make a little asterisk here and make a comment. When I have my students do this, I always tell them they need to do this on the side, because this really isn't a proper way to write the mathematics. But doing this over on the side lets me get this identity here very, very quickly, and I won't make silly mistakes. For instance, switching cosecant and cotangent from side to side. So take the time, it takes about 2 seconds to do this on the right, and then bring back the real identity that you need and put that into the line of mathematics that you're trying to work on.